If you place a pile of gold coins next to a freshly cut block of raw sodium, your eyes will tell you they belong to the same family of materials. Both have a distinct, lustrous shine. Both are dense, solid, and undeniably metallic. But drop them both in a glass of water, and that physical resemblance vanishes. The gold sinks to the bottom and sits there indefinitely. The sodium immediately explodes, reacting so violently with the water that it produces enough heat to ignite the hydrogen gas it is actively releasing. When we think of metals, we typically think of their physical traits. We expect them to be malleable, meaning we can hammer them into thin sheets. We expect them to be ductile, so we can stretch them into wires, and sonorous, ringing with a clear tone when struck. Inside a metal, positive metal cations are packed closely together, surrounded by a shared flowing cloud of delocalized negative electrons. This sea of electrons acts as a flexible buffer, allowing the atoms to slide past one another without breaking. Nonmetals, like carbon or sulfur, lack this internal electron mobility. Their electrons are locked firmly in place. Because of this, if you hit a piece of solid sulfur with a hammer, it doesn't bend, it shatters. Nonmetals are dull, brittle, and terrible conductors of heat and electricity. Relying on surface appearance can be misleading. Iodine is a nonmetal, yet it has a distinct metallic shine. Mercury is a true metal, but it remains a liquid at room temperature. Physical traits provide the first layer of identification, but to understand how these elements will survive in the real world, we have to look deeper. We have to measure how they interact chemically. Chemists organize that chemical behavior into something called the reactivity series. This is a strict descending hierarchy that ranks metals by their volatility. At the very top are the high-energy metals, potassium, sodium, and calcium. These elements are so reactive that simply exposing them to oxygen in the air can cause them to catch fire. You don't even need to heat them up to see a reaction. Drop these metals into freezing cold water and they rip the molecules apart to form alkaline solutions, releasing pure hydrogen gas in the process. As we move down the ladder, we find the workhorses of industry: magnesium, zinc, and iron. These metals are more stable. Throw iron into cold water and it ignores it completely. To force a reaction, you have to scorch it with superheated steam. When submerged in dilute acids, these middle-tier metals don't explode. They steadily sacrifice themselves, shrinking down as they slowly bubble away and release hydrogen. A metal's exact position on this descending ladder dictates precisely how fast it will surrender its electrons to the environment. This hierarchy also enforces a strict rule of dominance between the elements themselves. A more reactive metal will always physically strip away the chemical bonds of a weaker one. We can see this play out if we drop a piece of solid iron into a solution of copper sulfate. Because iron sits higher on the reactivity ladder, it forcibly displaces the copper, taking its place to form iron sulfate. You can watch this microscopic theft happen with the naked eye. As the reaction runs, the bright blue copper sulfate liquid fades to a pale green, and a layer of pure displaced copper completely coats the iron. If we reverse the experiment and drop pure copper into iron sulfate, nothing happens. Copper sits lower in the hierarchy and lacks the chemical strength to displace the iron. This process is called a displacement reaction. By testing every element against the others, scientists used this mechanism to measure and confirm the precise order of the reactivity series. Because the top and middle tier metals are so reactive, they are continuously bonded to their surroundings. This means you will never find a pure chunk of natural iron or zinc sitting on the ground. Instead, the earth holds them locked away, combined with oxygen, sulfur, or carbon. When a mineral deposit contains enough of a metal to be extracted profitably, we call it an ore. Breaking those natural bonds requires massive energy. We subject the ore to roasting and calcination, processes that use intense heat to force out the oxygen and other impurities. The conditions change completely at the very bottom of the ladder. This is where we find the noble metals: silver, platinum, and gold. These metals are almost entirely inert. They do not react with water, air, or most acids. Because they refuse to bond with other elements, they survive intact, allowing humans to pluck them from the earth completely pure. The reactivity series maps these elemental tendencies. It dictates exactly how much heat and chemical intervention we have to deploy to rip a specific metal out of the ground. Even after we extract these metals, nature immediately tries to reclaim them. We call this slow deterioration corrosion. If you leave refined iron exposed to moisture and atmospheric oxygen, it rusts. The environment forces the iron back into a brittle, oxidized state, which eventually destroys the material's strength. To maintain our infrastructure, humanity engineered a way to bypass these natural limitations. We created alloys. An alloy is a homogeneous mixture of two or more elements. By dissolving zinc into copper, we create brass. By mixing iron with nickel and chromium, we produce stainless steel. These mixtures allow us to enhance the base metals. They increase hardness and tensile strength, while creating a chemical surface that can resist the oxygen and water that cause corrosion. The reactivity series highlights the specific vulnerabilities of each element. By learning to navigate these elemental hierarchies, we transition from simply collecting what nature provided to engineering the materials that sustain our cities and technology.